Hello everyone, my name is Aidar, and in this video exercise 8 implementation of hydrological model part 1, I will show you the model setup in RS Minerve. First of all, we need to prepare our shape files because the RS Minerve model creation tool uses the GIS files to create a model. Let's look at our HRU shapefile in QGIS and open attribute table. It needs to have important information in three columns. The first column should be the name of elevation band. Second column should be the elevation of elevation band. And third column is the junk down information on the junction down the basin. In other words, outlet of this basin. In our case, it's the discharge station 17461 in the end of Zerafshan Basin. And this information in Junktown should be identical in the HRU to the information in the shapefile for gauge. Gauge shapefile contains the ID of this gauging station 17461 and the river ID, Zerafshan river ID, which is also identical to the information in the river shapefile where we have the downjunked information on the gauging station, river ID, Zerafshan, and that's all. Information in the shapefiles should refer to each other so the RS Minerve could connect them. The order of the columns is not important. Most importantly, you need to have clear and understandable names for the columns. For example, downjunked column can be first, second, or third. It doesn't matter. You just need to name this column something like down junk or junk down, so it would be clear to you that this column contains the junction down the river or down the basin. In the shapefile HRU, in the column junk down, we have the same information for all elevation bands. It is like this because we don't have subbasins in this Zerafshan basin. Since there are no subbasins, all elevation bands have the same outlet. It is the 17461. If we had additional subbasin, we would have additional junction with a different code, and we will have something like Zerafshan upstream and Zerafshan downstream. For example, we would have two different subbasin for Zerafshan upstream and Zerafshan downstream, and they would have different names. For example, Zerafshan upstream 1, Zerafshan upstream 2, etc. And they would have two different outlets for each subbasin. Once shapefiles are ready, it's important to reproject them to the local projections. For example, right now it's 4326. And we need to reproject it using the vector tab, data management tools, and the tool called reproject layer. Here in the input layer we specify which layer we need to reproject, and the target CRS we need here to choose the local projection. In our case right now is 32642, and you need to specify the location for the file, and after that you can run it and we would have reprojected shapefile HRU. We reprojected it to the UTM projection, so we need to call it something clear, for example HRU UTM. And you may ask why we need to reproject the layer. So I created a model with a non-reprojected layer, and here we can see the parameter A, which represents the surface area for elevation bands. And as you can see, the value for surface area of elevation band is 0 square meters. And the RS Minerve couldn't correctly calculate the surface area from global projection. And this problem happens not only to HPV models but also kinematic wave object, where RS Minerve calculates the length of the river. And this huge Zerafshan river is definitely not 6 meters. That's why we need to reproject from global projection to the local projection, and that way RS Minerve could correctly calculate the surface area. Next, we need to prepare junction or gauge shapefile, and this shapefile need to have two columns. First one is the junction ID with the ID of this gauge or junction, and the river ID, the ID or name of the river. Names of these columns can be different, but they should be understandable and clear to you that this column contains junction ID and this column contains the river ID. And in the same way, we need to reproject this shapefile from the global projection to the local projection. Go to the Vector tab, Data Management Tools, Reproject, and do the same steps. Next, we need to open the river shapefile and make sure that we have correct information in the attribute table. The junk down or down junk column should contain the ID of the gauging station that we have down the river and the river ID Zerafshan. In our case, we have only one river, Zerafshan. That's why we have only one row, Zerafshan, that goes to the junction 17461. And let's open two attribute tables at once for river shapefile and gauging station shapefile. And we need to make sure that they have same information on junctions and rivers. And you need to note that in the studies where you don't have sub-basins or you have only one basin, it's not necessary to have a river ID in the junction shapefile because there is no river going down from the junction, from the gauging location. If we had more rivers or more basins, then we would have additional information in the gauge shapefile, and this river ID in the gauge shapefile would have a different name. Next, we have another issue with the river shapefile. If we look at it, we see this river shapefile is too detailed. We have too many small streams connected to the main Zerafshan River. Depending on the basin, depending on your study case, you may leave all these small streams in your shapefile, but in this case, you need to remove these small streams because they may not exist in real life. So to be safe, we need to remove them. You may ask why we need to do that. So if you open the RS Minerve, for example, the kinematic wave object, we see the length parameter here. And this length is derived from the shapefile that you upload to RS Minerve, and RS Minerve would count every little stream in the shapefile to calculate the length of the Zerafshan River. Since we want to be as accurate as possible, we need to edit shapefile using the toggle editing and click on the vertex tool, and you need to choose all the non-existent or unnecessary lines for the river, select them and press delete. If you are unsure whether to leave some parts of the river or not, you can open OpenStreetMaps or Google Maps to see where the river is going. And sometimes after this kind of edit to the river shapefile, it has a problem. In order to check this problem, you need to open the attribute table and check the amount of rows. And the amount of rows should be equal to the amount of rivers that you have. For example, we have only one Zerafshan river, then we have one row. In case if you have a lot of rows for the same river, you can go to the vector, geoprocessing tools, dissolve, and input layer choose the river shapefile and save to the dissolved layer. And after the dissolve, you will have only one feature for one river. And lastly, you need to reproject the layer to the local projection. And after that, we can go to the RS Minerve and use these prepared shapefiles to set up our model. Open the RS Minerve, click on the GIS tab, add layer, and add all the layers that you prepared. HRU layer, gauging station layer, and the river shapefile. All of them should be reprojected to the local projection. And do not bother visualizing, choosing the right colors and visualization of GIS files in RS Minerve because you will not need that, and for visualization you would probably use the QGIS or ArcGIS. So after you upload it, go to the Creation tab, click on that, and now we will choose the configuration for subbasin. For subbasin, we need to choose the layer name. In the layer name, we will use the column of the HRU subbasin. Now we use the HRU without glacier UTM name and the basin name, the name. The links is the column junk down. It's where we connect our basin to the junction. Next, we need to have our optional properties. There, we need to click on the altitude Z and use the Z column or different name where you have elevation. And optionally, you can have the zones. In order to add zones, you need to create a column zones in the attribute table of HRU. I will quickly show you how to do that. Let's say you want to divide your basin into upstream zone and downstream zone that have different characteristics. That's why you need to divide them. You need to open your HRU shapefile, and let's say you want to divide it from elevation band 1 to 4 it's downstream, and from 5 to 9 is upstream. You need to create a field called zone, and you need to come up with some ID name, for example just one letter U and letter D for zone downstream or whatever. You the name should be clear and understandable for you. But now we don't do that. Next, let's create junctions. We need to specify the layer name for junction shapefile. Next, we need to specify junction name where we have junction ID. Then we need to have a links from junction to river. And links from junction to river is the river ID column. Next, the river shapefile where we have the names and connection from junction from river to junction. And then we need to allocate our subbasins. We choose all the elevation bands, and for this case we will use the HPV models. You need to choose the first elevation band by left clicking on it, scroll down and hold shift and left click on the last one. This way you will choose every elevation band that you have and then click on the allocate subbasin button. By selecting all the subbasins and allocating the subbasins, you will choose every elevation band to be the HPV model. But if you decide to have a different models for different elevation bands, you may choose, for example, one elevation band, for example, 0.9, and choose a different model, for example, GCM model for snow, and allocate it for the one different um, elevation band. But we will not use that. For our case, we have all HPV models. And for river types, we allocate the kinematic wave. Now we can create model. Click the button create model and the notification creation model finished will appear. If it appears, then you have successfully created a model from the shapefiles. And now we can go to the new model tab where we can check our model and we can see that we did something wrong because we don't have proper connections between the model, and we can see that we made a mistake in the junction ID. We chose the river ID instead of a junction ID. That's why the understandable and clear names matter, and you can easily find which column to use in the shape file. And after we do that, we change the mistake and we need to delete all the objects in the model. After that, click create model again and check our results. And we can see that this time the model creation worked well. Except one thing, we have a double connection between junction and kinematic wave, but it's very easy to fix. Just delete one connection. And this double connection happened because we only have one basin, and in the river section we can see the links from river object to junction, and this connection should go to the next junction of the different subbasin or basin. So if we had a different study case with a two basins or at least two sub-basins, we would have it differently. Next, if we need this kinematic wave, we can leave it and connect to another junction. And if we don't need this kinematic wave for the model, we can just delete it. Next, let's go to the cosmetics, click on the background and choose the load background and choose the any picture that you want. In my case, I will load the screenshot that I made in the QGIS with the digital elevation model of the Zirafshan River Basin. And I will just locate the HPV models and virtual stations more aesthetically pleasing. And now with this background, you can screenshot this model and add it as a figure to your research paper or report. Next, we need to check the length and the surface area of each elevation band. For example, in the kinematic wave, we check the length of the river, and in the HPV models, we check the surface area, the parameter A. And as you can see, we have a much bigger value than previously that I showed because we reprojected the shapefile to the local projection. And you need to check this surface area and length values because sometimes machines, computers, they make mistakes and you need to double check this surface area values for each elevation band. These kind of mistakes do happen, so be careful and double check. Next, another important part of RS Minerve, the database. In order to get access to the RS Minerve database, you need to click on the database tab. If you already have prepared database, you just need to click open in the upper left part and choose the database and load it, and you have loaded your already prepared the database. But what if you don't have the database? So you need to follow these steps. Click on the green plus add and you successfully created your first database. Then you need to click plus again to create a group which will contain a certain type of data. For example, let's create a group historical observation and put the category to inputs. Then press on the green plus add again to create a dataset. Here in the dataset, we will have actual data in the database. But we do not need to create a dataset with the zero values. We need to import the data from CSV files. So click on the historic observation group and then click on the import. We will have the folder appeared, and then you need to open the folder where you have the historic observation discharge data. But if you see nothing in this folder, but you sure that this folder contains this data, for example, like this, I have this data in this folder, but in the RS Minerve folder, it doesn't show up. You need to click on the file extension in the right bottom. Here we have RS dataset DSX, but we need to change it. Click here and choose the CSV extension or all files. And now all files will appear. And choose the CSV file historic observation RS Minerve. Double click on the needed file and it will appear in your database. Click on the drop down to see all the data contained in this dataset. And we can see we have 10 datasets, Заводхоза with the discharge data with the category flow, units cubic meter per second, and interpolation constant before. You may choose a different interpolation type as you want, but I usually use the linear interpolation for discharge. But different types of data, different cases, they require different approaches in this interpolation. So it really depends. And to see the data, you can choose the graphics tab or values tab to see it in a graphical form or a tabular form. So next, let's see the station Zerafshan 1, which has XYZ coordinates of its location and elevation. And inside of this station, we have two datasets of temperature and precipitation. So we will use this data, but before we start, we need to import another dataset to the HistOps group. We import the glacier discharge, choose the all files again, and locate the glacier discharge folder. Then import it, and here we will have the discharge data for a glacier runoff. I will explain later why we add glacier discharge separately in the database and not computing it using some models inside of RS Minerve. Also, later on in the next videos, we will need the future simulation data. So if you already have that in the folder, you may add them to the different group called future simulation. So I showed you how to add a database, then I will delete it and open the database that I already prepared for this video. After you import all the data to the database, don't forget to save this database so you will not do the same job every time you open RS Minerve. If you want to import your own CSV file, I can show you the structure of the CSV that is imported to RS Minerve. You can see here the first column is the column with the dates and the names of some parameters. For example, the station name, X, Y coordinates, Z elevation, the sensor type, category, for example, temperature and precipitation, and units of this data. And it's important to specify the sensor type because it would be very informative for you later on to know which column is precipitation and which column is temperature. Then we have a category that is very similar to the sensor type information and the units where we have Celsius and millimeters per day. That's very important one because sometimes data comes in Fahrenheit and we need to specify that. then the interpolation type, and after that we have all this data. And if you go to the database and open the time series, you can see all the configurations, all the parameters that are the same as we specified that in the CSV file. Specifying configurations in CSV is much faster way than clicking for all elevation bands for all data in RS Minerve. And one column here is one separate data set or one elevation band, or is it called here one station. And in one CSV file, you can mix up different data sets. For example, right now we here have the temperature data, precipitation data, and discharge data in one CSV file. But I generally do not recommend putting everything in one CSV file. For example, like we have here, it's better to put different data for different purposes in a separate CSV files. For example, put temperature and precipitation data in one CSV file and discharge data in a different CSV file. However, our current project is not very big. We have only one basin and only 9 elevation bands and only one discharge station with a measured data. And in this case, it's okay to have all this data in one CSV file. And for bigger projects, you need to have a better data management than just putting everything together in one CSV file. Also, if you have a different resolutions for data, you will need a different CSV files. For example, in one CSV file, the monthly data and different one for decadal data. So let's go to the next step of the model setup, and it's the data source on the left. And here we need to specify the group and data set for station and source. So when it says the station, it means all these virtual stations on the model. Station 0, station 1, 2, and etc. And here we need to specify the group where we put the data for virtual stations, the temperature and precipitation data. So click on the group and choose the observed group where we have temperature and precipitation data for virtual stations. You can always check the location in the database, so click on the observed group and click on the dataset histops RSM. In the database, you can check it. It's the same location. So, and then we have our station data located in the data source table. Next, we need to locate the sources. The same way we need to locate it. Uh, but since we have everything in the same database, we will have the same location for stations and sources. So it would have the same observed group and the same hist ops RSM dataset. We can check this in the database. After we locate the data sources in the table, we need to go to each data source object and choose the series identifier. Glass runoff is for glacial contribution, and the Ravathosa is for source object that is connected to comparator. Now let me explain why we have glacial contribution in the form of source object. There are different ways to represent glacial contribution in RS Minerve. For example, you can use the GSM model inside of RS Minerve, but if you think that GSM model is not enough and it cannot adequately represent the glacial contribution in the basin, then you can calculate the glacial contribution separately outside of RS Minerve, for example, using R, and then add these results to the RS Minerve using the source object. Like in this case, I calculated the glacial contribution using R in the previous videos, and then I exported the results to CSV file and then imported the CSV file to the database of RS Minerve. And here we have our calculations of the flow and then added it to the source object inside of RS Minerve. And by looking at the connection, the glacial contribution go to the junction where the glacial contribution will be combined with the results of HPV models and then will go to the final junction, the, result junction. And another source shows the observed values. It goes to the comparator, which is connected by the target source reference, and the result junction is connected to comparator with a target Q simulation. So it means that in the comparator we have two types of discharge, the simulated and the reference data in green simulation and reference in blue. And don't worry if you don't have such graphs right now, because I already run the model and it works, but in your case it may not work right now. Next important part of the model is the solver, where we specify our simulation period. We have the start and the end of the simulation. We need to put the start at the year and the date where we have our data available. After that, we specify simulation time step. If you have computational powers and the input data with a finer resolution, you can choose a different simulation time step. For example, 1 second, 1 hour, and 1 minute. But usually I have a daily data, so I use the simulation time step 1 day. Next thing is the recording time step. It is the resolution by which your data is being recorded. If you compare your simulation data to monthly data, then choose the 1 month recording time step. If you compare to daily, pentadal, or decadal data, then you need to choose a different recording time step, for example, 1 day. So let's see the difference how the recording time step 1 month and 1 day looks like. Press the validate. If the model is valid, then start the model and click at the comparator to see how the model looks like. We have here two lines, green one for simulated discharge and blue one for reference. It is the measured discharge. If you click and hold the mouse wheel, then you can select a certain area that you want to zoom in this graph, and let's zoom in into 1 year of data and see how the monthly recording time step looks like. Next, let's switch to the recording time step 1 day and see the difference. And we will see the difference only for simulated one, because we changed the resolution only for simulated values. The measured resolution is not changed. If you don't know which recording time step to use, just use the same recording time step as your observed data. For example, if you have monthly observed data, then use recording time step 1 month. Additionally, I want to remark that in small projects like this Sirafshan River Basin, we do not need any river objects such as kinematic wave object. And you can safely delete kinematic wave object and directly connect the junction to the comparator. We do not need kinematic wave object in this case because it has very little influence on the model. Also, there is a general rule to go from simple to complex. That's why we do not use the river objects at first, and if necessary, we can add it later. That's all for today. If you have any questions, you can write it down in the comments or reach us via email. Thank you and see you in the next video.